Hello, everybody, and welcome to a webinar from Q-CTRL on the introduction to using robust control to improve the performance of your quantum computers. My name is Michael Hush. I'm the head of quantum science and engineering here at Q-CTRL, and I have with me the great...
I'm André Carvalho. I'm the lead for quantum professional services at Q-CTRL.
So this is one of our first webinars. We're actually in the same room, so you get to see our lovely faces right next to each other. So today we're going to be doing a presentation on robust control. For those of you who have been attending all of our webinar series, this is actually a repeat of some of the content we used previously. But I think today most of you are new. It's great to see many new faces in the list. So how the talk is going to be structured, we're going to go for around an hour. At any point, you're welcome, if you have a question, to use the Q&A function as part of Zoom. Please don't use the chat section, as that will be just reserved for if there are any kind of technical emergencies, which I'm sure we won't have. But what we will do is, as we go through the presentations, there will be sections where we'll be able to answer your Q&A questions, and we'll go through them one by one. So just feel free to post them at any time. At the end of this webinar, you'll have the opportunity to click a link and fill out a survey. Please do, as this lets us know how to improve the webinars, improve our products. And if you complete that survey, you'll go into a draw for a $50 Amazon gift card. So there's something in it for you as well. And finally, after this, we are more than happy to follow up with a call to find out more about what your quantum needs are, what your quantum control needs are, and what quantum technologies you're using. So please let us know in that survey if you want to follow up or contact us in any way. So I'm just going to, how the webinar will be formatted today. There's going to be 4 sections. First, I'm going to give 2 on background, which were presented by me, on what the problem is we're trying to deal with. And I'm going to explain how noise in quantum computers affects the quality and performance of your results. Then we're going to talk about the solution we're presenting to that problem. And I'm going to show you how you can design and come up with robust controls in Boulder Opal and show you, at least in the theory, how they're going to improve the performance. And then I'm going to hand over to Andre, who's going to do 2 sections.
That's right. So in the sections that I'm going to present, we have 2 parts. And it's an application of the theory that Michael is going to explain in the first part about robust control. And that's the application of that on real hardware. So the first part is going to be about the design of those pulses for the IBM hardware, the IBM quantum computer. And the second part is the whole implementation, from picking the pulse that was designed to calibration and implementation in the machine.
Fantastic. So without further ado, let's get started. In this presentation, we are going to show how robust control can be used to improve the performance of a quantum computer. To start, we are going to illustrate the problem we want to solve. I have headed to the IBM Quantum Experience and set up a very simple quantum circuit. This circuit uses a NOT gate to change the state of the first qubit from a 0 to a 1. Then it performs a swap operation through 3 C-NOT gates. A swap operation switches the state of the qubits, making it a standard operation in many quantum algorithms. In this case, it switches the first qubit's 1 state with the second qubit's 0 state, and vice versa. Hence, if I wrote down the state of both qubits after the NOT gate, it would be 0, 1, and then after applying the swap gate, the state would be 1, 0. Now that I've made the circuit, I'm going to run it on a simulation and a real device. Let's have a look at the simulation results first. If we look at the histogram, the simulation returned a 1, 0 state 100% of the time. This is the ideal result of this quantum circuit. Now let's have a look at running the same circuit on a real device. When we look at the histogram from the real device, we see that we get the result 72% of the time. That's still the majority, but it isn't 100%. So sometimes we are getting an incorrect result of either 0, 0, 0, 1 or 1, 1. So why is our quantum circuit producing incorrect results when we compare real hardware to a simulation? The answer is noise. To get a better understanding of what this noise is doing and why this is occurring, we're going to look at the visualization feature from Q-CTRL's Black Opal. Here I have set up the same quantum circuit we had in the IBM quantum experience. Let's have a look what happens when I visualize this quantum circuit when there is no noise. Here I'm playing the dynamics of the quantum gates as a function of time. Each of these block spheres represents the states of the qubits, with the top of the block sphere representing the 0 state and the bottom of the block sphere representing the 1 state. Here we can see when we run the simulations with no noise, the qubits end in the expected locations, with the first qubit in the 0 state pointing up and the second qubit in the 1 state pointing down. We can also see the correct path the qubits are supposed to follow if there is no noise. Note, there is no movement in the entanglement tetrahedra in the middle of the visualization. They all stay at 0. Now let's turn on some noise and see if there's a difference. Black Opal allows you to visualize two different errors. One is if there is an error with the control amplitude, and the other is for ambient background dephasing. Let's turn them both on and see what happens. We are now playing the dynamics of the gates with noise. We can see that entanglement is now being generated in the entanglement tetrahedra in the center, while they remain 0 without noise. At the end, we can see the state of the qubits are not quite where they were before. When we actually measure the state of the final qubits, you project the state onto the z-axis to calculate the probability that the qubit will produce a 0 or a 1. Our qubits are not perfectly at the top or bottom of the block sphere, so they will not produce a 1-0 with 100% probability. Instead, we will also get 0-1, 0-0, and 1-1 results. This simulation shows that if there is noise present when we run our quantum computer, it will produce the wrong result at the end when we try to measure the final state. If we want to better understand these noises so we can fix them, we need to look at the effect they have on an individual gate. For the rest of the presentation, we are going to focus on the first gate in the circuit, the X or NOT gate. Let's first have a look what happens when I have a control amplitude noise and a NOT gate. Here we can see as we rotate the qubit, instead of going from the top to the bottom of the block sphere, we go a little bit further than we should. This is because the control amplitude has been possibly miscalibrated or is slowly drifting. This slight mismatch results in the final state being off where we wanted it to be. And if we keep repeating these gates multiple times, these errors add up and eventually we find the state a long way off where it's supposed to be. Now let's have a look what happens when we turn on ambient dephasing. Once again, we are trying to rotate from the top to the bottom of the block sphere, but the ambient dephasing creates a slight rotation about the z-axis, so we end up missing the final target state. Now that we understand what the problem is, noise on our quantum computer, we want to create a solution. To do that, we are going to use Boulder Opal. Boulder Opal is a cloud-based software solution that can be integrated into your quantum computer with Python. Here is a notebook that shows you how to program with Boulder Opal if you're trying to create a robust control. To start, we will do a simulation in Boulder Opal that replicates the errors we previously saw in IBM Q and on Black Opal. We're going to start by considering a single qubit with ambient dephasing noise. This model is a realistic representation of errors arising from stray magnetic fields affecting superconducting qubits. We first write down a Hamiltonian which explains how our controls and noise affect the qubit. In this case, the Hamiltonian is made up of two terms. The first one is an I modulation that comes through an omega I as a function of time that is multiplied by a sigma x operator, and the Q modulation comes through an omega q as a function of time, which is multiplied by a sigma y operator. We are going to try and achieve a NOT gate. The way we're going to achieve this is by turning off the I channel and only applying a drive with the Q channel. We're going to apply this at a maximum Rabi rate for a time of pi over the maximum Rabi rate. This will ensure that there is a rotation of pi, effectively creating a NOT gate. The next part of the Hamiltonian is the noise part. We are going to consider a stray magnetic field that is affecting our qubit. This is best modeled as a stochastic process eta as a function of time that is multiplied by the sigma z operator. The stochastic process eta is sampled from a noise power spectral density that obeys a power law. The precise form of this power law will depend on the type of noise. Q-control provides a set of tools for characterizing noise spectral densities like this. Picking the right noise model is essential when designing a robust control. We have a variety of different examples in our feature guides that are available on our docs, which go through many different types of systems and noise processors. Also, you can always contact us, and we are more than happy to talk through what system you are working on and what noise model is appropriate. Here is a plot of the particular 1NF power noise spectral density we're going to be using, which is quite common for stray magnetic fields. As you can see with a spectrum like this, the low frequency noise tends to dominate. This means that the noise itself will look approximately stationary throughout an individual gate, but will change slowly over multiple gates. Now that we have a Hamiltonian that describes our quantum computer, and explains how our controls and noise are coupled to the computer, we can perform a simulation. I won't go into detail on how to set up a simulation in Boulder Opal. For those details, please go have a look at the simulation feature guide. Let's skip to the simulation results. Here we are plotting the coordinates on a block sphere over time for a NOT gate. The thick line is the ideal simulation if there was no noise. We are doing a rotation about the y-axis from the top to the bottom of the block sphere to change the state from a 0 to a 1. So we can see that the x-coordinate changes between 0 to 1 to 0 again. The z-coordinate starts with a 1 and ends with a -1, while the y-coordinate remains fixed as it commutes with the operation. There are also dotted lines plotted. Each line corresponds to a different noisy trajectory. So each individual trajectory can be thought of as an independent time you ran your real quantum computer. In the y-plot, we can see there is actually quite a pronounced difference between the ideal simulation and the noisy trajectories, and the final state of the y-coordinate can be quite different from 0. To get an understanding of the average quality of this gate, we can have a look at the average gate infidelity. The average gate infidelity is calculated by taking an ensemble of noisy trajectories that I showed you before and averaging the distance, which is done by an overlap, between the target unitary we are trying to achieve, the NOT gate, and the actual unitary that was achieved by a particular trajectory. In this case, we can see that when we average many trajectories, we end up with an average gate infidelity of 0.0016. If you combine many gates in a particular quantum algorithm, the number of these errors is going to accumulate quickly. It can be difficult to figure out how a particular control will be affected by a noise process, especially when it has complicated spectral features in its noise power spectral density. To get a quick understanding of the quality of your control in terms of its robustness, we can have a look at the control filter function. A filter function gives you an understanding of how sensitive a control is to noise at different frequencies. The filter function is defined as the magnitude of the Fourier transform of the noise operator in the frame of the control. The noise operator in the frame of the control sounds complicated, but basically what it's telling you is if you were moving along the state of your qubit as the control was applied, it would tell you the current direction the noise is having an effect. With this definition of the filter function, it's possible to prove, when the noise is small, that the gate infidelity that I introduced to you earlier is approximately equal to the integral of the noise power spectral density multiplied by the filter function. This indicates that the filter function tells you how much of an error will be produced by noise at different frequencies. We can calculate the filter function using Boulder Opal. If you want more details about this, go have a look at the filter function feature guide. Here we can see the filter function of the standard NOT gate we simulated above. You can see that it is flat for low frequencies. This indicates if we have noise at low frequencies, they will have a negative effect on the average gate infidelity. Not only can this filter function framework be used to understand how robust a particular control is, we can also use it to optimize and design robust controls. This is what we're going to look at in the next presentation.
Hello again. Let's answer some questions. So we had one question that came up during that presentation. I'll also set up a poll just to get to know you a bit better. So I'll run that now, and we'll look at that at the end of the Q&A section. So we had one question about, let me just click Q&A.
I can get that for you, Marco. So the question is about if there is a reason why you didn't include the drift Hamiltonian in your simulation.
Yeah, so in this particular simulation, we just assumed that you were doing the experiment on resonance, so that you've calibrated the frequency of your drive beforehand. And in that case, all you have to do is program the envelope of the modulation on top of that on resonance part, so the drift goes to 0. But you can easily set up Boulder Opal to deal with whatever drifts you want. And we were doing simulations with multiple qubits for recently, weren't you? We were doing parametric gates.
That's right.
Yeah.
So on that, I mean, following up on that question, maybe could you comment on the limitations or what can you do in terms of different Hamiltonians in?
Yeah, so currently you can, we'll go into later about the way that you can set up Hamiltonians. You can set up Hamiltonians with any number of qubits, any number of channels. So you can have multiple control channels. The qubits do not have to all be in resonance. They can have different frequencies, different drift Hamiltonians. You can also add a variety of different type of control lines. So you can add bandwidth limits. You can add whatever kind of constraints you happen to have on your real devices. Pretty much at this point, you can program anything that your imagination can come up with. But if you find a limitation, please contact us, because we're constantly also expanding the functionality for the Hamiltonians.
So we have a couple of more questions here coming up. So unlike simulation, on a real device, we need to do tomography to acquire the final quantum stage. Is this what needs to be done before using the optimization?
Maybe you'd be best to answer that, because we'll be talking about calibration actually in the later presentation.
Yeah, that's right. But I mean, for the optimization itself, we don't really need to do the tomography, right? So the optimization is done based on the model that you have about the system. So the tomography really comes down to when you need to actually determine whether your gate is working properly or not.
Yeah.
So we'll be talking more about the implementation in the next part. There's a question here about how do you sample the noise spectral function as?
Yeah, so there is an additional feature available in Boulder Opal, which actually allows you to do a series of experiments to determine what the noise spectral density is. And so using that is really as easy as you pick the particular noise spectral density you want to identify, if it's dephasing. Q-CTRL then we've got a package which provides you a set of pulses. So you do a set of pulses to your qubits. You basically do some dynamical decoupling style sequences, which tell you information about the dephasing process. And you do a simple set of measurements at the end of each pulse to determine where the qubit state is. You then can feed that information to our Python, our Boulder Opal Python package, and it will use that information from the experiments that you've done with your real quantum computer to determine the noise spectral density of your system, which can be then fed into things like the optimization process. So the really cool thing about that is that you can actually use the qubits themselves as the detectors to figure out what's wrong with your device, which means you can be assured that you're measuring the actual noise that they experience. I would say that you can also just, like, if you happen to have a data sheet for one of your devices, so if you happen to know that your particular noise signal generator has a dephasing process on it and it's in the spec sheet, you can also just take those samples out and put them directly into the package as well. Cool. So let's now, we've established the problem. I'm just going to end that poll and have a look at the results. So hopefully everyone can see that here. It's good to see we've got a bit of a mix. So what's your main area of interest, I asked first. And we've got most people interested in doing research on quantum technologies. That's great to see, you're in the right place. We're happy to help. And so, yeah, we've got also some people primarily looking at improving the performance of quantum computers, and that will be the focus of today's talk. But yeah, the few people in the room who are doing quantum sensors, just wanted to highlight that a lot of the things that we talk about today are also relevant to improving quantum sensors, because you typically also want to maximize the number of atoms that you're transferring between your states to do detection. And so there's a lot of actual connections there. And please contact us if you want to hear about that more. And then finally, what hardware access do you have? So most people doing theoretical work. That's interesting to see. So I did want to highlight that everything you see today can also be used for theory. And we have probably we've got some new updates coming through for our simulation tools, which will make them probably one of the most sophisticated tools for doing simulation of the dynamics of quantum computers. So yeah, there is a lot of use for theory as well. But then otherwise access through cloud quantum computing hardware. And on that, so in order to use the controls we're talking about today, you need pulse level control, which is like low level where you can program the individual pulses. Andre will talk about that more. So that's currently potentially possible with IBM. And there was actually an announcement between Rigetti and Q-CTRL recently as well.
That's right. So Rigetti also released the pulse level access. It's still not available to the general public, but they said it will be in the near future using AWS.
Yeah. So this pulse level control is becoming more and more common. And yeah, you should, if you want to use these controls, you just need access to cloud hardware with pulse level control. And of course, a lot of you have your own hardware, and then I assume you can kind of do whatever you want with it. So let's end this section. Again, thanks for using the Q&A function. Any more questions you have, please keep putting them in. Let's move on to the next section.
We have established the problem. Noise in a quantum computer interrupts the path of a standard NOT gate, and this results in a bad average gate infidelity. Now we will create a solution. We will design a new robust NOT gate that is immune to the negative effects of the noise. We can design this pulse using the optimization feature in Boulder Opal. The optimization feature does a search over lots of different candidate pulse shapes until it finds one that minimizes a quantity we call the robust infidelity. The robust infidelity is a number that quantifies how close a particular candidate pulse is to the correct operation and how robust it is. It is made of two parts. The first part is the control infidelity. This quantifies how close the gate made by the candidate pulse is to the target gate. When the control infidelity is 0, the gate made by the candidate pulse is the target. The second part is the noise infidelity. The noise infidelity comes from the filter function framework and is essentially the filter function value at 0 frequency. If the noise infidelity is 0, then we can be confident that any low frequency noise will be strongly suppressed and not affect the average gate infidelity. Hence, if we can find a candidate pulse with a robust infidelity very close to 0, it will implement the gate correctly and it will be robust to low frequency noise. Programming Boulder Opal to find a robust pulse is simple once you've written down the control Hamiltonian. The optimization feature requires that you create a graph that relates the pulses that you are trying to optimize to the control on your qubit. I have mostly created this graph for the problem we are considering now of a qubit under dephasing noise. Let's go through this step by step. I've written down the total Hamiltonian again so it's easier to refer to. As we put together the graph, we are rebuilding the control Hamiltonian and then separately adding the noise operator. The first part that makes up the control Hamiltonian is the omega I. This is basically our pulse that we need to optimize. We created a function above which will make it a bit more convenient. We provide this function with the total duration that we want to apply the pulse for, the number of segments that make it up, the maximum Rabi rate that can be achieved, and also we give it a cutoff frequency to ensure it doesn't change too quickly. This pulse is defined as a piecewise constant function. Each segment of it has an amplitude and duration. I create two signals, one for the I part of the modulation and one for the Q part of the modulation of the microwave drive. The next thing we have to do is connect how these signals couple to the qubit. In other words, we have to multiply them by an operator that operates on the Hilbert space. I've already written down the code for the omega I times sigma x part. We create a piecewise constant operator instead of a piecewise constant signal. This takes in the signal that we had before and then an operator, in this case, a sigma x. Coding the operator that connects the Q modulation to the sigma y operator is very similar. Let me just copy paste this. The first thing we have to do is change the name of the variable to an I and then a Q. Next, we have to change the signal from our I pulse to our Q pulse. And finally, we have to change the operator from being a sigma x to a sigma y. The last step in creating the control Hamiltonian is to simply sum these operators together. The noise operator in this case is simple because it's not related to the control signal. All we have to do is create a piecewise constant operator with a sigma z operator. We have constructed our control Hamiltonian and noise operator. So the last part is just to feed these operators in a function that creates the robust infidelity. The robust infidelity takes the Hamiltonian, which is our control Hamiltonian, also the noise operator as defined above. You can have multiple noise operators, so we will allow it to be a list. And lastly, we will also define the target unitary. In this case, we are trying to do a NOT gate. To complete the graph, we use the infidelity piecewise constant function. This combines all the parts of the Hamiltonians and the target to create a robust infidelity. We are now ready to do the optimization using the calculate optimization function. We provide the function with the graph we created earlier and also provide it with a set of labels that indicate which part of the graph corresponds to the infidelity we want to minimize, which we call the cost node, and the labels of the pulses we want to export, which we call the output nodes. Executing the calculate optimization function spins up an ensemble of processes in the cloud which search over many candidate pulses. The function then returns the smallest cost it found and also the corresponding outputs. We can see the cost it got was 1.6 times 10 to the minus 10. This is very close to 0, which indicates the output pulses will do the correct operation and will also be robust. If you run an optimization and your cost is not close to 0, it's most likely that the particular constraints you have are too restrictive and the optimizer is unable to find a good cost in the search space. To give it a better chance, you should consider relaxing your constraints. One of the key ones is increasing the duration. As you can see here, we have a duration which is 3 times as long as the standard NOT gate. This is because creating a robust control is typically much more complicated than creating an optimal control. Now that the optimization is completed, we can plot the pulse that was found. Here you can see 2 plots for the I and Q modulations. As you can see, the pulse is made up of a set of small piecewise constant segments. This is typically what you need when you're programming these pulses on real signal generators. The other useful feature here is that we have added a bandwidth limit, so you can see that these pulses are smooth. This is particularly important when implementing these pulses on superconducting qubit quantum computers, which tend to have tight bandwidth limits on their pulses. We can now investigate and confirm these pulses complete the correct gate and are robust. First, let's have a look at their filter functions. I'll skip the details on how to create one and just look at the result. Here we can see the filter function for the robust case we just made in pink. You can see that it suppresses noises at low frequencies and has a very, very small value with frequencies less than 10 to the power of 2. The final test of this control will be looking at a full simulation with the original noise model. Once again, you can look at the simulation feature guide if you want to find out details on how to implement this in Boulder Opal. Here we see a simulation of multiple trajectories of noise on a block sphere. As you can see, the state no longer moves on a simple straight path, but rather a bendy one because the pulse we are applying has a more complicated shape. Nevertheless, if we look at the trajectories, unlike before, where at the end there was a significant divergence between the solid line and the dotted lines, indicating that the noisy trajectories were not arriving at the correct final state, we can see here that they all converge, and the final state after the noisy simulation is close to the final state if there was no noise. We can confirm the robust control is robust to the noise by having a look at the average gate infidelity. Here we can see that the average gate infidelity when we use the robust control is significantly better. The NOT gate has an average gate infidelity of 0.0016, while the robust gate, on the other hand, has an average gate infidelity of 0.0004. This is a significant improvement. We have successfully used Boulder Opal to design a pulse that is robust to noise. We have verified that it works by looking at a filter function and simulation. But one final question remains: why did it work? To get an understanding of this, we can move to a geometric picture. During the optimization process, we minimized the robust infidelity. A component of the infidelity was the filter function at 0 frequency. It's easy to show that minimizing that value is the same as minimizing the integral of the noise operator in the control frame over the total duration. You can think of the noise operator in the control frame as the current direction of the noise as you move along with the control. If the direction of the noise happens to integrate to 0, then any noise process that is almost quasi-static for the total duration would effectively self-cancel. We can see this explicitly by looking at a graphical representation of the noise operator in the control frame. This operator happens to be traceless and Hermitian, so you can represent it simply with 3 numbers corresponding to its overlap with the Pauli matrices. In this plot, we've plotted the Pauli matrices X, Y, and Z versus time for the noise operator in the control frame. We can see as we move along in time, the noise is changing direction. At the start, the direction of the noise is entirely in the Z direction, but by the time we were halfway through the pulse, the noise has completely moved to the X direction. Now there is very little noise moving in the Z or Y plane. The key thing to note is if we look at these plots, the area above the curve is equal to the area underneath the curve. That means that when we integrate along each of these lines, they will all equal 0. This ensures that any quasi-static noise, no matter what direction it is in, will effectively self-cancel as we complete the operation. This is why sometimes this effect is called an echo when talking about dephasing on a qubit. Now let's complete the loop. So I started this talk by looking at this quantum circuit. We examined its performance when looking at an ideal simulation versus real hardware. We noticed that noise was creating an issue. Sometimes the results were wrong, and then showed you how to design robust controls using Boulder Opal for an individual gate. In fact, I showed you how to design a robust control for the first gate in this circuit, a NOT gate. If you then did a drop-in replacement where you used our robust control instead of the standard control for the gates in this algorithm, you would get a significant improvements to the robustness of these gates to the noise, and hence the accuracy of your final results would improve. In the next presentation, we will show you how we have implemented these robust pulses on IBM-Q and seen real improvements to gate performance.
Welcome back. So we had one question which came up, which I want to address. So the question was, what optimization algorithm is used? So what we do is we actually use a gradient-based method, which does many, many optimizations. And as I mentioned before, we spin up multiple processes to kind of do them all in parallel. That's sort of one of the more powerful things about this graph-based approach. So by letting us define things as a graph, we can actually use special techniques to analytically then backpropagate the derivative of the actual control connection between your variables and your cost function. And that allows us to very efficiently find solutions. So we've done benchmarking. When you compare the optimization, say, compared to just Q-tip on one processor, we get an order of magnitude improvement in speed. And then combining that with our cloud infrastructure, we can get over, in the limit of some larger quantum systems, we've seen improvements over a factor of 100 compared to other software packages for doing optimization. Yeah, so...
A couple of more questions here. So about the filter function. So can you explain the behavior of the filter function at the high frequency limit? And does that matter?
Yeah, so what you tend to see is as the filter function increases, when you get to around the Rabi rate, you tend to see when you've designed a control which suppresses low frequency noise, around the Rabi rate limit is when the filter function starts to, again, noise will have an effect, and you see the filter function rising up. And then after around the Rabi limit, you see that the filter function goes down again, and that indicates a kind of a self-cancellation effect. So what's that showing is that if you have noise which is moving more rapidly compared to the time that the control takes, it tends to self-average a bit and have less of an effect. So what we find is that the filter function framework is particularly useful for noises which change slowly compared to, well, sorry, that's not true. The filter function framework can be done with anything, but the controls we're talking about today are targeted at gates where the noise changes slowly compared to the time of the gates. And that's what we tend to see on the real devices.
Right. And another question on that. I mean, in the first part, you were showing, for example, the spectral density, but in the optimization, I didn't see anything about that being input into the system. So how does that work?
Yeah, so what you do is what we are typically looking at is on real devices, you typically worry about systems with low frequency noise. And that's quite common. So the control framework allows you to put in low frequency noises. If you do have an application where you have a more complicated noise spectrum, that is possible to input, but just come talk to us about that and we can kind of figure out the best approach. Yeah.
Right. Then there was another question here about the validity of the filter function, if this has been shown experimentally.
Yeah, so this has all been shown experimentally. There is a paper by the Professor Michael Biersick, our CEO, which was published in Nature Physics in 2014. Yeah, and if you follow up with us, we're sure to have happy to supply you with that link. But all of the things that we're showing today have been verified experimentally, both in ion systems, and today we're going to be showing you more results with superconducting systems, and they've also been shown in a variety of different kind of cold atom systems as well.
Thanks, Michael. So one more just before we start the next part. So is this the same thing as quantum optimal control theory?
So the difference is optimal control theory only takes, so I talked about this cost function in that presentation, where you minimize the difference between the gate that you're trying to, the unitary of the gate you're trying to apply. That's what traditional optimal theory does. What's different here is we also make it robust. So that means we have that additional cost function element, and that means that if you implement under a real device, not only will it achieve the right operation, it'll achieve the right operation even in the presence of noise. And so what you tend to find is when you try and use optimal control theory on these real devices, because you often don't know certain parameters perfectly, so you don't necessarily know the exact frequency of your qubits, or perhaps there's an issue where you don't understand the exact coupling, or it might be changing over time. When you try and use optimal control theory on these real devices, often it doesn't get implemented right. So one solution is robust control. But the other thing which will be relevant and is quite useful is you can also calibrate online. And we have a new feature coming up for automated optimization, which allows you to calibrate and get things working rapidly on a real device. And Andre's presentation will talk a little bit about how to do that calibration now.
We have a couple more questions coming up. So one is, can you add constraints on the shape of the pulse while optimizing?
Yeah. So you can add whatever, you can add constraints to the magnitude of the pulse, the bandwidth of the pulse. You can add an arbitrary linear filter, so you can put a high pass or low pass filter in between your system. Yeah, you can effectively add whatever constraints are relevant to your real device. And if you have a particular exotic constraint, come talk to us and we'll talk about how you can adjust that through a package. Yeah.
We should move on.
Yep. Let's go through. So let's start the next presentation.
In this presentation, we will learn how to create pulses that work on real hardware. You'll be presented to a set of optimization tools that allows you to include information about device limitations to design pulses that are fully compatible with hardware constraints. And since we are talking about pulses working on real hardware, let's start with some of our recent results of robust pulse running on the IBM Cloud quantum computer. Here's a side-by-side comparison of the IBM native pulse and a Q-CTRL pulse robust to amplitude noise over the course of 4 days. The pulses are implemented in parallel in all 5 qubits in the chip. The robust pulse provides a 10-fold improvement in hardware stability over time and across device, as well as a 10 times improvement in single qubit gate performance. We will discuss in this presentation all the steps necessary to achieve these results, from pulse design to calibration and implementation. Let's start with this diagram representing a simplified model of the different stages of what you would encounter while trying to optimize a gate. On the left, you have a gate that you want to apply on the system, and to perform an optimization, you need access to the pulse that will physically implement that gate. At the hardware level, this pulse will be generated by an arbitrary waveform generator, go through control lines, and finally reach the qubit. For now, let's be at peace with our ignorance about the hardware and consider the very basic model that we may have to consider for the quantum system. We have a control Hamiltonian representing the physical interaction that performs the gate, with gamma being this complex shape of the pulse. Alternatively, it can be written in terms of I and Q variables, which is more common for superconducting qubits. Here, we are writing this Hamiltonian in terms of Pauli matrices, as we are modeling the system as qubits, but we need just to take note that sometimes a better model for the system is including more levels, and that can be included in the Hamiltonian for your optimization. Finally, we can add extra terms defining the noises that may be acting on the system. Here we consider the phasing, described by this term with the sigma z operators, and also some noise on the control amplitudes. Now that we have the model for the control Hamiltonian, as well as the noise that we want to suppress, we can give this information to the Boulder Opal optimizer to find the desired gate. The diagram on the left shows the steps of this process. We input the parameters of the system, like the maximum Rabi rate and the hardware time resolution. We also input optimization parameters, like your target gate, its duration, and also the number of segments that you want in your pulse. Then you create the Hamiltonian with the optimizable variables, in this case, I and Q. If you want to generate a robust pulse against a specific kind of noise, you add this term as well, and you are ready to run the optimization. Here, in this presentation, I'll be focusing on this high-level description of the optimization, but you can find the full code and all the examples we will cover in this presentation in the application notes in our documentation. So in the center figure, you see the result of an optimization of the phasing robust pulse. On the right, you see the result of the implementation of this pulse on an IBM quantum device. The experimental points clearly deviate from the expected numerical curve, indicating that something is not quite right, from our original pulse to the final effect. So a clear feature of this particular optimized gate is this fast variation and abrupt changes in the pulse values. Given that the hardware electronics have bandwidth limitations, one may conclude that this pulse may not be properly implemented in the device. So one option to solve this problem is to use Boulder Opal flexible optimizer, because it allows you to include extra constraints to deal with hardware limitations. In this case, for example, we want to avoid the abrupt changes of the previous pulse. One way to do this is to impose a bound on the amount of change that can happen in the pulse value from one segment to the next. This adds a simple step in the optimization flow shown on the left. So that's this part here. The resulting pulse is smoother than before, and its implementation shown on the right is visibly better as well. Now, we could take a different approach to smooth our pulse and avoid these high frequency components of this highly varying pulse. So we can do this by including a filter. This is described in the Hamiltonian on the left. We apply some linear filter on our variables I and Q. So again, this can be easily incorporated in the optimization flow on the left. The pulse obtained is smooth and suppresses frequencies above a given cutoff that's user-defined. You see again a good agreement between the experimental data and the numerical simulation. This diagram here summarizes what we discussed in the previous slide. So we use information about hardware constraints, in this case, the bandwidth, for example, of your waveform generator. One can design a pulse that's compatible with your device. Now, there is yet another use for this filter feature of our optimizer. So after the program pulse is created by the waveform generator, it then travels through control lines until it reaches the qubit. In this process, the pulse can be distorted according to the channel's transfer function. This means that the pulse reaching the qubit is different from the one that you designed. This would lead to bad results. However, if you know the transfer function of your control lines, you can add this information to the optimizer, which will then find the pre-distorted pulse that will lead to the desired pulse shape reaching the qubit. Now that you know what the flexible optimizer is capable of, I would encourage you to go and explore our application note on constraint optimization. It contains multiple examples of what I covered today and much more. There's a version that you can access in our documentation, but also a Jupyter notebook that you can execute if you sign up for our free trial. So in summary, Boulder Opal has a series of features that allow you to refine your optimization based on information of your device. But now, what happens if you don't have this kind of information? How can you take advantage of pulse shaping on someone else's quantum computer? We'll discuss this in the next presentation.
That ends the next presentation. So we had a couple of questions about that. And so Andre, how do you know what filter bandwidth to use to smooth your pulses?
All right, so if you have access to your own hardware, you could just use that information. You measure the transfer function, for example, and can input, have an idea of how your waveform generator generates that. In our case, for example, in the example I showed with the IBM was basically on our experience. Mm-hmm. So we knew that the ones that were varying quite rapidly, they were not giving good results. So we imposed some boundaries, some cutoff frequencies there. And in the beginning, that was kind of testing based on the measurements that we had in the system. But that's also something that we could use, for example, our identification tools and characterization tools on the device, that we could measure how the device responds to those pulses to come up with the frequency that you have to kind of use as a cutoff.
Yeah, exactly. Yeah, you can actually the system identification feature, which we won't talk about in detail today, but yeah, you can identify these things. I think in the interest of time, we might move on to the final presentation, which will have some more results, and then we'll answer the rest of the questions.
In the previous presentation, you learned how to create robust pulses that are compatible with your device by adding real hardware constraints to the Boulder Opal optimizer. In this presentation, we'll discuss what to do when such information is not available, as is in the case when you're running your gates on someone else's quantum computer. To achieve good results in this scenario, the secret is careful pulse calibration. Let's start our description of calibration using the example of pulses being implemented on a real device. We'll be using IBM Q as it allows users to design their own gates on some of their chips using Qiskit pulse. The Q control pulses that we discussed in the previous presentation were given in terms of the physical quantities I and Q. The IBM software uses a different input. Those are dimensionless quantities varying between -1 and 1 that I'm calling here AI and AQ. So your first task is to map the real amplitudes I and Q into the hardware inputs AI and AQ. For that, we first select a given value of AI and send a constant pulse with this amplitude into the system. The qubit will be excited, and by varying the amount of time the qubit is exposed to this drive, you observe the system performing Rabi oscillations, as you see on the left. You can then fit the experimental points and extract the value of the Rabi rate corresponding to your original choice of hardware input, as it's shown here in this plot on the right. So you picked a value on the horizontal axis, did the fitting, and found which value on the vertical axis they correspond to. You now repeat the same procedure for another value of AI, another point in the horizontal axis, and by performing another fit, you find the other value. And by doing this for all the range that you want to calibrate, you establish this mapping between the Rabi rates and your dimensionless hardware input. So one advantage of this calibration is that it is general in the sense that it's valid for any pulse, as we assign a value for each pulse height. You can then verify your calibration by taking one of your pulses and implementing on the device. In this case, I used the dephasing robust pulse, here shown on the left, that we discussed previously, and its time evolution is shown on the right in terms of the three components of the Bloch vector. You can see that there is a good agreement between experimental data and the theoretical prediction. So even though this is a good indication of your initial calibration, to really test its accuracy, you should do a different experiment. The experiment I'm referring to is repeating the gate multiple times. If there is an error in your initial calibration, this pulse repetition will amplify its effect and help you recalibrate the gate. So in this plot, we show the experiment done for the IBM D4 X gate and our dephasing robust pulse. You can see the quick drop in fidelity for the robust pulse, but you can also see that it recovers later on. This is an indication of coherent errors as illustrated in this diagram on the right. The red curve shows Rabi oscillations, but if your pulse under-rotates slightly, this error will add up and look like the oscillatory curve, similar to the experimental results. So the question is, how can we fix this? To get a better idea of what the pulse is doing in the system, we added a scaling factor to our pulse and scanned it for multiple pulse repetitions. So this is described by this equation at the bottom here. You can see that the results for the experimental runs shown on the right are close to our numerical simulations on the left, being a little bit more different in this central region here. The white dashed line corresponds to no scaling. That is, we are back at that original Rabi rate calibration. For the numerical solution, this coincides with this band of high fidelity for a wide range of pulse repetition. For the experimental results, this looks shifted. And to take advantage of this band of high fidelity, we have to rescale the pulse up to this scaling factor shown by the dashed pink line. If we now run the pulse again, but now rescaled by that scaling factor that we just found, we see that not only we get rid of that typical miscalibration curve, but that also our pulse outperforms the default IBM gate. So this successful calibration is really encouraging, but does it always work? Well, it doesn't. This plot illustrates the same 2D scan as before, but now for a pulse that we designed to be robust for both the phasing and amplitude noise. The numerical solution shows a broader band of high fidelity, as you would expect for a pulse that was created to be less sensitive to fluctuations in its amplitude. The experimental result, however, shows a completely different picture. The pulse reaching the qubit is very different from what we planned. Let's look at what may be going on. We have the pulse that we created, we send it to the hardware, and the evidence is that it does something else, as if it were a completely different pulse. As we have discussed in the previous presentation, hardware constraints can deform pulses before they even reach the qubit. Before, we explored how our knowledge about the hardware can be used to design better pulses. Here, we don't have this choice. Well, since the effect we're trying to do is undo pulse distortion, the strategy here is to use a two-parameter differential calibration. We call it differential calibration because it allows the I and Q components to be scaled relative to one another, deforming the pulse. So after obtaining this relative scaling, we perform a second step, so it's a second overall rescaling to maximize the gate fidelity. The hope here is that this differential calibration fixes the deformation induced by the hardware. So before I move on to show results of those pulses in the real hardware, I'd like to again point out to our documentation and specifically for the application notes that we have on calibration. It has all the codes and all the steps necessary to run a pulse calibration on the IBM Q device. And if you go to app.qcontrol.com, you'll find an interactive version that you can execute if you sign up for a free trial. So let's then go to the results that we get from those calibrated pulses. So the results in this plot show the successful calibrations of 3 different robust pulses. One that is robust against the phasing, another one that's robust against amplitude, and a dual robust that's simultaneously robust to those 2 kinds of noise. They again beat the out-of-the-box IBM default pulse. The curves in the plot indicate a fit using this function here at the bottom, so which allows us to extract both the errors coming from rotation, written as this epsilon here, as well as exponential decays. So once with these errors at hand, we can estimate an overall error per gate as illustrated in this plot here. So the points are the error per gate on a given day for the phase and amplitude robust pulses, as well as for the IBM default for all 5 qubits in the Valencia backend. So the pulses were applied simultaneously in all the qubits, and we see not only perform improvement from our pulses, but also a homogenization of errors across the device, meaning that all qubits perform similarly under the robust pulses. Finally, we come back to where we started, a plot that summarizes the improvements from our robust pulses. The difference between the bright colors on the IBM pulse as compared to the homogeneous dark colors, meaning low errors, for the Q-control solutions is very evident. It shows in a single plot the overall error reduction with robust pulses, the spatial homogenization of errors across the device, as well as calibration stability. Note that the Q-control pulses were calibrated only once. They were calibrated on August the 3rd, while the IBM pulses are calibrated daily. So this completes the model-based optimization part of our webinar. You have been introduced to the tools necessary to create robust pulses that work on real devices. If you have information about device imperfections, you are now in condition to include the relevant constraints in your own optimization to design better pulses. If you run your gates in someone else's quantum computer, you can use the calibration strategies discussed today to successfully implement your pulses in these devices.
Hello again. So we have a couple more questions that just came through. The first is, are the only pulses you can implement a piecewise constant? Is there other ways of implementing pulses?
All right, yeah, so there is, in our simulations, for example, we can use the continuous versions as well, and also in the optimizations we can do an optimization that's, instead of using the segmentation, we can use, for example, Fourier bases, and then use the continuous version of those pulses in the optimization. Yeah.
So basically, if you can write down a function that you want to parameterize your control out of, you can put it into the optimization package. So we have another question that just came up. Do these error reductions contribute to the quantum volume metric reported for qubit performance?
Right. We haven't done any explicit calculations of the quantum volume on that, but that should reflect on not only on that, but also on the performance of actual algorithms.
Yeah.
If you take, for example, so the example that we showed today was single qubit gates, and they are of course part of more complex circuits. And I believe we have simulations, for example, for VQE.
Yeah, we've done simulations for VQE where we've seen if you implement our controls and there are errors like that we have seen on real devices, then you will get improvements and get more accurate results. Quantum volume, of course, is similar. So as long as you have all of the appropriate controls, you'll get an improvement. And we are continuing to work actually on implementing these results for 2-qubit gates on devices.
That's right. Yeah.
So we also had one question about, are you open or interested in collaborations with academia in the US? If so, what would be the best way to contact Q-Control?
Yeah, I guess that's something, I mean, just contact us to discuss
we
things
work
in that direction.
We have a variety of different institutions across the US who use our software. And we also provide some assistance when you purchase our software to set up and get things going. So we do collaborate with many institutions in the US and around the world. And we have offices currently in Australia, the US, and looking in towards Europe as well. So you pretty much have someone from Q-Control in every time zone if you want to contact us. Cool. I've got one more question coming through. Do you have open positions for internships? So I might just answer that one quickly. Yeah, so we currently don't have an internship program, but you should still feel free to come in contact with us and we can have a quick chat. But we do have open positions in a variety of different roles on the side of product development and also quantum engineering. So if you are heading towards the end of your PhD or you've got a lot of experience and want to continue working in the dynamic quantum control industry, yeah, please come talk to us and have a look at our careers page at Q-Control. Cool. So with that, I think we don't have any more open questions. So I'll just, again, at the end of this presentation, you'll be invited to fill out a survey. Please do. It'll let us know how we can improve these webinars and also get you into a draw for a $50 gift voucher. And after this, if you want to see any of the demonstrations that Andre did, where can they go, Andre?
They can go to docs.qcontrol.com just to look at the documentation that we have. But if you want to sign up for a free trial, then you can, as I said in the presentation, you can go to app.qcontrol.com. And then from there, we can actually open up the notebooks and use our Jupyter server and run and make changes and see how it works by yourself.
Yeah. And if you've got an account with IBM Q, for instance, you can replicate every result that was shown today.
That's right.
On the real device. Yeah. So every week we of course also completely open. So we show you all the code that we use and you can figure out how to do it yourself. Great. Well, thank you very much for attending, and hopefully you'll come into contact with us afterwards, and we'd be happy to take a phone call to talk more about your quantum needs. So,
all right. Thank you.
Thank you.